Hi, welcome to another edition of linear algebra. Today we are going to talk about determinants. Let's go ahead and take a quick look at this topic. This happens to be a very lengthy topic, but we are going to shorten it to what we need. I'm going to let you know about some of the properties of determinants, but we are not allocating all the time it needs for all the detail. So we have already seen definition of determinant in the 2 by 2 cases and occasionally in 3 by 3 cases. Let me remind you that determinant of a 2 by 2 B matrix A, B, C, D, that was equal to AD minus BC. We saw that in the section on inverse of matrices and some other places. More importantly, we saw it in the section on finding eigenvalues and eigenvectors. Now we want to talk about this thing in a lot more detail. So suppose you want to calculate the determinant of, say, 2, 3, and 4, and let's say 7. What do we do? So 2 times 7 minus 3 times 4, and that happens to be 14 minus 12. Well, that is 2. Well, first we want to explain some way of visualizing determinants, something that makes sense to us from other areas of mathematics, so that it doesn't look all just algebra or arithmetic. But truly speaking, determinant is a complicated topic, and sometimes people write an entire book on that. But we are just going to shorten this to just items we do need. One way of explaining determinants in terms of geometry is in its relationship to length, area, volume, and such things. So for example, here we are looking at a matrix which is made out of several columns. So there's 2 columns here, 2, 4, and then 3, 7. If we go ahead and graph this, now I'm going to do this thing quickly and not precisely. So 2 and 4 could be somewhere here. I'm not going to draw it. It's not going to be a good drawing. So I draw the matrix, the vector 2, 4. And then I draw the other one, which is 3 and 7. So 3 and 7 is going to be way up here. So let's draw it in some other color. Say this is 3 and 7. Now something about these two vectors gives us 2. What is that? Very simple. If you make a parallelogram out of these two, the one I've drawn is becoming a bit too narrow, but that's fine. This parallelogram has an area, okay? That area is just that determinant, 2. You can go ahead and calculate the area the way you have learned to calculate the area of right triangles back in middle school, and you are going to see that it actually boils down to 2. Interestingly enough, there is another way of doing exact same thing. That is, you can take 2, 3, 4, 7, and this time you can look at 2, 3, and then 4, 7. So you can draw this vector and that vector, and that's going to be a different parallelogram. In that one also the areas too. I'm going to leave it to you to draw and perhaps check that it is so. Well, of course, every now and then the area turns out, the determinant turns out to be negative quantity. So for example, if I had 2, 5, 3, 4, that's going to be 10 minus 12, it's going to be minus 2. Of course, areas in geometry, we typically don't consider it as negative. So what turns out to be true is that the determinant of a matrix, of 2 by 2 matrix, is either positive or negative of this area. It depends on which vector comes first and then second. And that is something that you also see in the cross product of vectors. You remember in the cross products, long time ago we had the cross product. If you had a vector A and another vector B which are sitting on a plane, then the cross product of them is a vector that is perpendicular to both of them. And at that point we also mentioned that the length of this vector is equal to the area of this parallelogram. The length is equal to that area. And of course, if you have b times a becomes negative of this, points to the other way, but the length is still the same. Okay, what we want to do is to extend this idea and extend the formula to bigger matrices. Smaller matrices is actually very easy. If you have it 1 by 1, well, kind of sounds silly to talk about a 1 by 1 matrix, but rest assured that the determinant of a 1 by 1 is just whatever number you got there. So if determinant of 5 is 5 and the determinant of minus 7 is 7, so you can think about this thing as a length. Think about this thing as the area. Next comes up, what about the 3 by 3? A, B, C, D, E, F, G, H, I. Well, what do you think? This is length. It attaches itself to the concept of a length. This one is the concept of the area. For 3 by 3, what do you think it connects to? Well, if you say volume, you are our grand prize winner. Yes, it relates to volume. How so? Well, you can apply the same idea like here's a vector, here's a vector, here's a vector, or pick them row by row. And then you have 3 vectors in space. Just so that I have an easier time of drawing it, let me choose some vectors that are kind of suggestive. So there could be one vector, and there could be a second vector, and then the third vector. Of course, they are not going to be always so nicely arranged for us right at the corner there, 90 degrees to each other, but just for sake of easy drawing and such. Well, when you have these 3 vectors, you can make a box out of them. So the way I drew it, the box looks like a cube and so on. It doesn't have to be. So in general, you're going to have, now it's going to be rather crowded looking. If I have some vector here, and then some other vector here, and then perhaps a third vector here, you can still go ahead and make a box. It's kind of a box that's kind of a bit crushed maybe, and at some peculiar angle and so on. So something like that. So I hope I'm conveying the idea. If you have 3 vectors in space, you can make a so-called parallel pipette, some sort of a box, like a crushed box or something. And the volume of that, plus or minus the volume of that, is going to be the determinant of 3 by 3. Now we want to go ahead after the formulas. course, when we go to 4 by 4, there we can't draw much of anything, but it's still true. Whatever that four-dimensional item is, it has a measure. So we have length, area, volume, and then you go to 4 dimension, and there's whatever that is. That is equal to the determinant of the 4 by 4, and that's how it goes. However, as far as the formula is concerned, things get out of hand pretty quickly. 2 by 2 is manageable. 1 by 1, of course, was trivial. 3 by 3, we have given some shortcuts before. But a major disadvantage of all these formulas you have seen is that they give you the wrong impression. They leave you with the impression that there is a shortcut. So when it comes to 4 by 4, students go ahead and apply some sort of a imaginary shortcut to it, thinking that that's how to get the determinant of it, and none of those things work. Determinant is truly a monster. There's kind of no shortcut to it. One major reason it's not all that favored in practice is just the complication of calculating it. We do use it in several formulas, for example, for finding eigenvalues and such. That's essentially only good for just those mini cases we are going to look at. More professional situation, people go after other techniques other than determinant. But it does have an illustrious past in history of mathematics. It does show up in many places, and that's a reason we are going to look at. Now, before we dive in all the algebra and all of that, let's have perhaps a little bit of an interesting trivia about determinants. Okay, so determinants, one person you would not suspect have something to do with determinants is Lewis Carroll. This pen name of Charles Dodgson, author of Alice's Adventures in Wonderland and Through the Looking Glass, and many other literary works. So he was actually a mathematician, lots of other things. He was a photographer, an inventor, and a deacon, and so on and so forth. He was actually a math professor, and one of his contributions is how to calculate determinants. So the issue is complicated enough for somebody to put his name on it for a certain style of calculating it called condensation method. And we are going to, you can read about it in the text. We are not going to mention that, but I just wanted to let you know next time that you're watching that movie For the Nth Time, you might remember that the author of the text actually had something to do with determinants. And some people speculate that all those weird things in his text, in his book, have something to do with the mathematics he was working on. At any rate, let's go back to our regularly scheduled program and see, okay, what do we do here? Okay, so let me remind you, a shortcut, and then emphasize only good for 3 by 3, not applicable. So here's a preemptive strike against that mistake, not applicable to 4 by 4 and 5 by 5 and so on. So the idea is that if you have a 3 by 3 A, B, C, D, E, F, G, H, I, you want to calculate the determinant of this. You duplicate the matrix, or at least the first two columns of it. So A, D, G, B, E, H. Or if you want to do a clean job, maybe go ahead and duplicate all of it. You have two choices. Then, kind of in the spirit that you had here, this minus that, we do something like that here, except that we have uh, 3 diagonals going this way, 1, 2, then 3, and then 3 diagonals going the other way, so 1, 2, and 3. Notice that if you go ahead on this diagonal, CEG is same as the CEG there, so that's the reason most often people don't bother writing this, but if you did write it, then you can use that instead of that one. Anyway, so we multiply the items on these blue diagonals and multiply them by +1, multiply items in the green diagonals and multiply them with -1, and that is going to be our determinant. So the determinant in this case turns out to be AEI. That is this. When I multiply it, AEI, and then I have BFG. So here's my BFG, and then CDH. So here's my CDH. And going in this direction, I have CEG, except negative, and then AFH, and then BDI, I believe, BDI. So we have 6 terms. 3 of them comes up with plus signs, 3 of them with minus signs in front of them. Each of them is a product of the 3 terms. And many of these attributes I just mentioned do show up in 4x4, 5x5, and so on, except that it gets to be a lot crowded and a lot more crowded, and that the size of the answer starts to grow rather quickly. Here's an indication of what we are facing. So suppose the size of the matrix I'm dealing with is 1 by 1. Well, what's the determinant of that? It just had the number of terms in it. So what am I referring to? We said determinant of a 1 by 1, it just has 1 term in it. How about 2 by 2? 2 by 2, it has 2 terms in it. Term is a product of a bunch of variables you have. So 2 terms I have here, 1 added, 1 subtracted. So I have 2. In the case of 3 by 3, here I look at the 3 by 3, I see that I have 6. What's your guess as to how many things I'm supposed to deal with in case of 4 by 4 or 5 by 5 and so on? Let me see if you can take a wild guess. This sequence 1, 2, 6 is a very famous sequence. Does it ring a bell in your mind as to what that is? Here's one way it goes. This is double of that. This is triple of this. The next one is going to be quadruple of that. It's going to be 24. And this one is going to be quintuple of that one. This is going to be 120. So this is 1. This is 1 times 2. This is 1 times 2 and multiply by next. And 1, 2, 3, 4. And then 1, 2, 3, 4, 5. Well, you see that we are dealing with some sort of a serious situation. You have never dealt, I'm pretty sure you've never dealt with any mathematical item with 24 pieces to it. That's an equation. On left hand side you write determinant of A. On the right hand side you have to write 24 terms. 24 terms. Each of the term is going to be now product of 4 items. 12 positive, 12 negative, meaning 12 of them come with a plus in front of it, 12 with minus in front of it, and that's what it is. There are no repetitions or anything like that. There's no cancellation that's going to happen. So 24, that's already looking intimidating. And imagine, go to 5 by 5, you're dealing with 120. That doesn't look fun. To have 120 things, that's already going to fill up a whole page. 120 terms. each of them made out of product of 5 numbers, 60 of them pluses, 60 of them minuses. Well, how does it go? 6 by 6, I have to multiply this thing by 6, becomes 720. If we get tired of this notation, we make another notation, 6 factorial. So those of you who have taken your calculus sequence, you remember factorial. 7 by 7, multiply this thing by 7, becomes 5040. You're gradually talking about something. You remember I called it a monster? So 5040 terms, each of them product of 7 entries. 2520 of them positive, 2520 of them negative, and so on. And it is what it is. There is no way of cutting it shorter or doing something to it. So you see what we are facing. Okay, so when we are giving you shortcut for these things, so you don't want to take it too seriously. It's like, okay, it's good for so-called baby cases, and then after that you're talking about some serious formulas. Okay, so with that correction, to hopefully nobody is going to think that there is going to be an easy way of doing these things, unless the problem is made to be super easy. You actually have to bite the bullet and go down through some serious calculation to get it. Well, how do people do it? There is there are several methods. One of them is Lewis Carroll's method. We're going to talk about that, but the one that is generally mentioned in most textbooks is the expansion method. So expansion method now it could be called the row expansion, or it could be a column expansion, either way, or a mix of them. This idea, we are mentioning it here, particularly useful to students in computer science because it has a style of calculation that actually has a name there. They call it recursive style. So recursive style, that concept by itself, the idea of recursion, recursive style perhaps is more important for you than the determinant itself. So what's the idea? Let's go ahead and explain it in the context of 3 by 3. So I write this thing. I'm not going to write numbers so that we don't get sidetracked by A, B, C, D, E. I forgot my alphabet, D, G, H, I. Suppose I want to calculate determinant of this. First, I go ahead and choose a row or a column. Amazingly, it doesn't matter which row or column you choose, always you end up at the same answer. In practice, you be smart and use the row or column that's going to make your life easier. We are going to talk about that later on, but right now just choose any row or any column. You have no reason to pick somebody else right now, so I go and say, okay, I pick this one. Now I'm going to write the elements of that row that I looked at here, space them out because I'm going to write a lot of other stuff. Next, I go ahead, make a checkerboard sign that starts with plus at the upper left and then flip-flops. I go and look at the same row of the table of signs, this checkerboard sign. Whatever row I pick there, I pick the same row here and put the sign that I see next to elements of the row I saw. Next, I go ahead, start looking at these things one by one. Let's look at the A alone. I go ahead, look at the A. Say, okay, let's go ahead and remove the row and a column on which A is sitting. Well, A is always sitting on this row, so that's going to be always eliminated. Now I'm gonna go ahead, eliminate that column. So, okay, there is a sub matrix left, that's EFHI. Original was 3 by 3, now it's 2 by 2. I go ahead and calculate the determinant of the 2 by 2. So I write here determinant of, still have to calculate that, excuse me, sorry, what was left for EFHI. Now I go ahead and do it with B. It's okay. Eliminate the row and a column on which B is sitting. Who is left? A 2 by 2 matrix made out of D, F, G, I. Okay, yellow and blue are taken out of the game. I have to calculate determinant of that smaller matrix. So D, F, G, I. And then repeat the game one more time. Let's see. Okay, this time go after C. Eliminate row and a column on which C is seated. See who's left. Take the determinant of that, D, E, G, H. Okay, 2 by 2. Either repeat this game again, or if you don't want to drive yourself up the wall, you can use that shortcut if you want to, whatever style you want. Now I said this, the idea itself is actually more important than the formula. Recursive style. What does that mean? It means I'm trying to calculate something that is of size 3 by 3. It is being reduced to a bunch of calculations of 2 by 2s of the same creature. So a function wants to be calculated, it's calling on itself, but calling on a smaller version of itself. Like this was 3 by 3 and that was 2 by 2. Presumably you know how to handle 2 by 2 and that's why you're going after 3 by 3. That style of calculation in computer science is very important. It's called recursive style, meaning calculating something in terms of the idea of itself at a smaller scale. Okay, at smaller scale, and then you go ahead and calculate it however you want to calculate it. So for example, you can say A times EI minus FH, then minus B times determinant of that. These things, let's do the shortcut on those. And the C, and this is going to be DH minus EG. Now you're going to say this is looking very different than what you were writing here. Well, it looks different, but when you open the parentheses, it's all going to be the same. And it's an amazing thing. It does not matter which row or a column you pick on at the beginning. So I just picked on the first row and put those elements out. But I could have picked, so to repeat this thing again, let's see, suppose I want to calculate the exact same thing, A, B, C, D, E, F, G, H, I. Now, let's suppose the one that we eliminate at all stages is going to be middle column. Now I go ahead and write the elements that I picked here, B, E, H. Pick the signs according to this sign table. So it's minus first, and then a plus, and then minus. So in this case, I am picking, maybe I should have used a different color here. That's a good idea. At any rate, you get the idea. So now I'm getting these guys to go with those guys. And then I say, well, okay, who is left? Left meaning what? So B in this column is always going to be taken out. First, I go ahead, take out this row. Who is left? All colored items are taken out. D, F, G, I is left. Again, next time around, let's see, I can remove this thing, and then, oh no, I didn't want to do that, sorry. See. D E, it was F for me, and then we had picked out this guy was taken out, and then I was gonna take the second row out. Is that right? That's what I was gonna do. Who's left? A C G I, and round 3. You tell me what should I write here, huh? So let's see, I'll be careful this time. This one, this is taken out. Who is there? A C D F. So this time I took out second column to begin with. Attach the sign that I have there to these entries, and then I took turn to pick out different rows. Now we have 3 mini matrices, sub-matrices. I calculate determinant of each of them, however, and then I get my answer. So you have 3 choices there, 3 choices here, 6 choices. It's amazing that every which way you do this thing, you end up with the same answer. And that requires a proof, and the proof of it is in your text, and it's a lengthy proof. We're not going to repeat it here, just mentioning. Okay, when you are doing the expansion style with specific entries, you still have to be smart about it. How do we become smart about it? So how do we become smart on doing these calculations? Actually, it's not so sometimes like playing chess and seeing down the road and such, but you can do the following. You have to do a lot of multiplication here, is that right? What is to your advantage? Your advantage is that one of these entries being 0. If it is 0, then you don't need to bother with the other determinant. You just know that ahead of time that whole thing is going to be 0, and as a result you have less drudgery to calculate. So for example, like what? So suppose I have 2, 3, 5, 7, 11, say 16, and say 0, 0, 1. Suppose we want to calculate determinant of this. So I just made up some example to show you how we are going to use the expansion method to our advantage so that we don't suffer too much. So what do? What we say, we're going to say it'll go after the row or a column that has lots of zeros. All else being the same, that's going to be the winning strategy. Go after the one that has lots of zeros. Why? Because when you want to write the expansion, you're supposed to write the first entry, the second entry, and the third entry, and then attach the signs to it. So you will attach, for example, plus, minus, plus. Then you're supposed to write the determinant of whatever is left. And determinant of whatever is left. But don't even bother with these things. Not writing, not calculating, because you are multiplying by 0 anyway. So this is going to be 0, this is going to be 0, and I have to only worry about the last one when this row and this column are taken out. I am left with just 2, 3, 7, 11. So 2 times 11, 22. 3 times 7 is 21. 1 times 1 is 1. And the determinant of this ugly looking matrix is just 1. So sometimes it pays to look at what you're dealing with and use it to your advantage so that you reduce the amount of work you have to do for calculating determinant. So when it's 3 by 3, you can't go wrong. But when the size increases to like 4 by 4, 5 by 5, this is only way that you can actually calculate something on this type of test type of questions to be able to do it in regular time. Otherwise, you'll be facing the dilemma of how to collect so many little pieces, and that's not going to be practical. So if you look at the big matrix, pretty much the only way to calculate anything is to pay attention to where are the zeros. Okay, so this is the determinant calculation. Now I'm going to write some properties of the determinant. As I said, people used to write entire textbooks, size of your textbook, just talking about determinants. It's kind of has fallen out of fashion, but some of the basic properties of determinant we still need to know because we are making use of them with respect to our eigenanalysis situation. So the way we are using it is the following. Uh, we need some indicators that tells us when determinant of a matrix is zero. So the question is, when is determinant of some matrix, let's call it matrix M, is zero. You remember that was one of the basic steps of eigenanalysis. We had the first step of subtracting lambdas from the diagonals and then setting determinant of that equal to zero, getting something that had a name to itself called characteristic equation. So that issue comes up here. Well, we can phrase the answer in many different ways. I'm going to write some general statements and some particular statements. One situation is when mx equal to 0 has non-trivial solutions. That's one of the steps we use with eigenanalysis. Another is when M inverse does not exist, or we say the matrix M is not invertible. If you want to apply the Gauss-Jordan elimination to it to get the M inverse, the process breaks down somewhere. There is no inverse to be found. Another way of detecting the determinant is zero is when a row is a linear combination of some of the other rows. Well, this might sound kind of theoretical looking. Let's go ahead and give some specific clues that makes a determinant to be easily detectable to be zero. One of the very easy cases that you can list here is an entire row is zero. Like meaning what? Like if I have A, B, C and then 0, 0, 0 and then X, Y, Z, determinant of such a thing is, you can easily see it to be zero. Just expand it on that second row and right off the bat it's of course is zero. Another easy way of detecting a determinant is zero is that two rows are identical. That of course means one of them is a linear combination of the other one. So the two rows are identical. Like meaning what? Meaning I know without calculating that if I have ABC and then again ABC and then anything arbitrary here, that definitely becomes zero. That's what it means. Slight variation on this, a row is a multiple of another row. So they are all baby cases of this case 3, meaning what? Determinant of, suppose I have a, b, c here and x, y, z here, and the first row, say, is a multiple of the third row, such as tx, ty, tz. This guy, the determinant is equal to 0, meaning I don't need to go through all that mess to figure out what it is. Right off the bat, I know the determinant is 0. So there are cases like this, we could list them, where the determinant is actually equal to 0. The one that comes out in the eigenanalysis case is this. This is what is used there, and like as a stepstone, that's what we use to actually make our argument. But then we go ahead and calculate the determinant however we can, and then you're done. Okay, next set of properties is, well, we said in our course the most important set of operations were the so-called elementary row operations. So we are going to talk about the effect of elementary row operations on determinant of a matrix. Maybe I should remind you what were these guys. By the way, before I go there, you see this word showing up everywhere. Row, so on, so on. Well, everywhere you have a row, you put a column across the board. You have to replace all the rows with columns. The statement is still true, so I am not going to be repeating myself. A column is a linear combination of other columns. It's just, there's no real difference between rows and columns. Okay, elementary row operation. What did we have? You remember we had 3 elementary row operation. Elementary row operation, we had addition type, which was the following: add a multiple of a row to another row. Sorry for my bad handwriting. So suppose I have a matrix M. Okay, again, let's go after our favorite letters: A, B, C, D, E, F, G, H, I. I make somebody else out of it. Let's, in mathematics, customary to decorate your original letter with something to say some relative of that. So this is tilde, M tilde, M whatever you want to call it, M tilde. Suppose I add, for example, 3 times row 1 to row 2. Has to be different rows. So what happens there? So I have A, B, C, D plus triple A, E plus triple B, F triple C. We are not touching the other. The question is, if I do an elementary operation of this type, what's going to happen to my determinant? That's actually a very crucial thing, the way the proofs are built for this topic. We are not offering the proofs, but let's offer the basis of those things. If I add a multiple of a row to another row, what happens? Here's the magic. Nothing happens. Determinant of M tilde is same as what it was. This is an extremely important property of determinants. If you add a multiple of any row to some other row, it has to be another row, it's not going to make a dent. That is the big star attraction of the whole thing. Okay, we had 3 operations. we had operation 2, which was a multiplication. So suppose again I have this m, and m tilde, suppose we are making 5r3. So m tilde now is a, b, c, d, e, f. I left my alphabets, I guess. 5g, 5h, 5i. What do you think is the deal with determinant of m tilde? You should be able to do that using the concept of expansion on this row. If you do expansion on that as opposed to that, what happens? Everybody is 5 times bigger, so it's not a big surprise that this comes out to be 5 determinant of m. Okay, that's rather trivial. Item number 3. Okay, what did we have? Addition operation, multiplication operation. Do you remember what was the third one? Do you remember what was the third one? So here's your incentive to go in the cupboard of your mind and tell me what was the third one. The third one was, of course, exchange operation. Suppose I exchange row 1 with row, so whatever, some other row has to be m tilde again. So I'm exchanging. So 1 comes into position of 2, 2 goes in position of the 1, and we are allowed in operation, this type of operation, we are allowed only one operation. So the question is, what happens to the determinant of this one? Care to guess? Well, make a guess. Always guess. Try to be ahead of the professor to check yourself. This happens to be minus determinant of what it was to begin with. So this is like we are shuffling the rows. Any exchange of 2 cards in your deck is gonna make your determinant to multiply by negative. So what's the advantage of these things? The advantage is that our holiest operation in this course was the Gaussian elimination. Our Gaussian elimination was made out of these 3 operations, so we can track what happens to our matrices and its determinant, and that way, that would be actually the most practical way of calculating determinant of a matrix that's made out of numbers, is to apply the Gaussian elimination and track your determinants until you come to a matrix that's easy for you to just calculate what the determinant is. I mean, you hit the identity at the end, and determinant of identity, well, guess what's the determinant of identity? That's going to be 1. Okay, so some other properties. Properties that the way we mention it in mathematics, we go back to the operations that we have in mind and ask ourselves, what do those operations do to our this new concept? Like here we had the operation of elementary row operations, and then we are asking to see, well, what happens to my determinant if I do any of these things? And the magic is that it's very straightforward. So what other operations we had? We had, well, addition, multiplication, transpose, powers, we have everything. So how about determinant of a plus b? What is the determinant of a plus b? Well, you go try and then you get stuck. What is determinant of a plus b? Nothing easy, nothing pops out, nothing that I can mention here. So let me just say nothing easy comes out of this, except for one situation. If there is something very special about A and B, if A and B, they are same except for one row, like what does it mean? Like A is, again, A, B, C, D, E, F, G, H, I. And B is A, B, C, D, E, F, and this is what say X, Y, Z. If everything except one row or one column are identical, yes, what you like to think is true. In that case, you can say determinant of A plus determinant of B. That's really trivial by expansion on the third row, doesn't really say anything. So in general, we can't do anything. Item number 2, determinant of A times B. Okay, multiplication, we don't write anything. When you say, if addition, I couldn't do anything, multiplication, sure, I shouldn't be doing anything either. No, it so turns out, perhaps one of very complicated theorems to prove at this stage, is that this thing does what you think. So we have a kind of falling rocks here, but this one is doing what you think it should do. Well, out of this you can extract all sort of stuff. For example, determinant of A squared is going to be determinant of A times another determinant of A, which is going to be then determinant of A squared. By same reasoning, determinant of A to any power, any positive power, is going to be determinant of A to that power. It even works for negative powers. If A inverse exists, then determinant of A inverse is equal to the determinant of A to power of -1, which you can write as 1 over determinant of A as you want. So this formula is valid for all integer exponents so long as the right hand side makes sense. Okay, so that was a good surprise. How about transpose? Transpose is one of the easier cases. Determinant of A transpose is same as determinant of A. Once you accept the expansion theorem, this one just pops out right away. Okay, so these are some of the properties of determinants. You are going to see them in the various problems that you are going to encounter, and so I hope you just read the text, read all the examples in the text, and you allow me to cut this lecture short. Already kind of a long lecture. So once again, determinant is a complicated topic. There are books on that, but we just limited ourselves to what we need and what's okay for a course of our scope. So until next lecture, good luck and God bless.